how to apply unstructured and structured pruning, retrain the pruned model, and measure performance trade-offs. The speaker for this workshop would be Rafael Subo Ayap. He is currently a third-year computer science student at De La Salle University under the BSMSCS Honors Program. He is also a tutor with the Peer Tutor Society and a member of the Center for Computational Imaging and Visual Innovations. His current research focuses on the optimization of deep learning models for counting small objects, with a particular interest in mosquito egg detection as a tool for vector surveillance and public health. So I'm now giving the floor to Rafael. Rafael, you may start your presentation.
Thank you, Sir Aaron. So first, to start, I'll send the Google Drive link just so everyone can have access to it. Then I'll start sharing my screen. Hi. So this is the technical workshop on hands-on pruning of computer vision models in PyTorch, which is a continuation of my academic lecture last week. So yeah, pruning is a practical technique for reducing size and computational cost of deep learning models. For this specific workshop and notebook, we're gonna train a baseline CNN. We're gonna apply unstructured pruning, then structured pruning. Then throughout it, we're gonna fine tune and retrain the prune models and also evaluate the different trade-offs and just visualize what happens during pruning and unstructured pruning and structured pruning. So one of the main outputs I want from this, what I want everyone to see is what really happens. I want us to know how to visualize pruning, and so that when you're working on like a model yourself and want to prune it, you'll know how to check the metrics and which to look for, and which to see is like important. So first in the notebook, yeah, we'll just set up important libraries. So we'll import PyTorch, Torch Vision, and pruning utilities. So PyTorch has a pruning module. Then we use the Torch Vision Transforms module to import the CIVI dataset. So if you have CUDA installed and it's able to use it, that's what we'll be using for training. So for this first block, we load and prepare the C410 dataset. If you check the Google Drive link I sent, it doesn't have the dataset we'll be using because this code block already downloads it from Torch Vision. So yeah, C410 contains 60,000 images. It's 32 by 32, very small, across 10 classes. So yeah, here we apply normalization also to prepare it for training for it to work better in our CNN. So we already have the split of the trained dataset and the test dataset we'll be using. So if we run this, we'll be loading it already, and we can see that the training we have is 50K of the 60K. Then the test samples we have is 10K. The classes are 10. So there's airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. Next, let's define our CNN architecture. So this is a very simple CNN only for this workshop. So we'll create a simple CNN with 2 convolutional layers and 2 fully connected layers. So this is our baseline models. So we have here the conv1, our first convolutional layer. It takes 3 input channels. So this is the RGB. Then it outputs 32 feature maps with a 3x3 kernel, as we see here. Then convolutional layer 2, or conv2, takes the 32 feature maps, then expands it to 64 feature maps with, again, 3x3 filters. So we have a pooling layer also. So max pooling with a 2x2 kernel, which is going to be used to reduce the spatial dimensions by half. So a 32 by 32 becomes 16 by 16, then 16 by 16 becomes 8 by 8. Next, we have the fully connected layers, our FC1 and FC2. So yeah, we have the 64 feature maps of size 8 by 8. Then we flatten it into 128 neurons. Then the next layer, the 128 neurons, outputs are 10 classes, 10 values, because it's 10 classes for our task. Then we'll be using the ReLU for our activation functions. other than our last activation function, which will be softmax, as we'll see in the training, because it's a multi-class task. So yeah, let's run this. So we load our simple CNN. Then I just wanted to show the parameters, the number of parameters we have, because that's the important part of what we're going to do when you're pruning. You're going to try to reduce the number of parameters. So yeah, for convolutional layer 1, it's conv1, 864 parameters. Conv2, the weights is 18,432 parameters. The FC1 weights are 524K. The FC2 weights are 1,280. You can see how since FC1 has 524K out of 545K parameters, you can see how the fully connected layers have most of our parameters. This will be shown, like it will be shown why. This is why I chose this for the rest of our workshop. I also put in the notebook some of the calculations, just if you're curious. So to calculate for the convolutional layers, it's the input channels, which is 3, then the output channels, 32, then the kernel height times the kernel width, so 3 by 3. Then for linear layers, it's just the input features times the output features. So it's always important to visualize our sample images, especially when we're new to the data set we're working on, to see what we'll be working with. So we just we just have a code block to run, to load the images, then to just show the first 8 images we have. We can see that it's very blurry since the CFAR10 is only 32 by 32 pixels. We're like stretching it out here. That's why it looks very blurry. And it shows that this data set is a good benchmark. It's not like impossibly hard, but it's not like super easy too. So yeah, we can see a picture of the ship, the tier, then these other few images. So I also have here just functions for training the model and a simple evaluation function also. So we use a cross entropy loss. So kind of standard for multi-class because it penalizes very confident wrong predictions, while it more heavily than those like uncertain predictions. Then the optimizer will use this Adam. So for the training process, it will be for each epoch, basically, we're going to iterate through all the batches of our data. We move the data to our device here. We're loading it, the inputs and the labels. Then we zero out the gradients. We do the forward pass that we defined before in our model. Then we calculate the loss. Then we do the backward pass. Then we like update the weight. So the optimizer will just automatically adjust it to reduce the loss. Then we just track the running loss and we print it while we're training. For this simple evaluation model function, we're basically just for each batch, we're just getting the correct predictions, the number of correct predictions, and we just return accuracy as a percentage. So let's just load that in. For this model, for this workshop, for the notebook I gave, it will train the model itself for 6 epochs. But since it's just, I'm just trying to demo it right now, I have it saved already in a baseline model tab. So yeah, this model was trained for 6 epochs, and we can see that the accuracy is 71%. So this is because it's just a simple CNN, and also it's only a few epochs. So it's not going to be that accurate. So yeah, we just have here to save the function, to save the model. Then I have a function here, another helper function to count the parameters. So yeah, when you count the total parameters before we do any pruning, we can see that the sparsity is still 0%. There's no non-zero parameters because we haven't done pruning yet. So yeah, as a total, we have 545 K 98 parameters. So yeah, one of the main things I really want to show is visualizing what happens. So before we do any pruning, let's visualize what the weight distributions look like, so that we can see what happens after, what's the differences. Then yeah, we can see for some of our layers, there's like a distinct bell curve. For most of them also, like for FC1, then FC2, then convolutional layer 2, we see that most weights here are they're most frequent near 0. None of them, as you can see here, so it's 0 out of 864 are like actual zeroed out parameters. but a lot of them are very close. So these are either like 0.0001, negative 0.0001, or like around those like type of values. So yeah, I just had code here to just count the zeros and just plot the histogram for it. Now we can start applying our actual pruning. So step by step, first thing we're gonna do is we're gonna load the unpruned model first. Then we're gonna like make a copy of it. Then we're gonna try to prune every layer we have. So the convolutional layers, the two of them, and our two fully connected layers, are FC1 and FC2. So this is gonna be L1 unstructured pruning, meaning we're gonna remove weights with the smallest absolute mean. So absolute values, yeah. So it's the smallest absolute values. So those closest to zero, as we see here, a lot of these are gonna be pruned. So for this line, you're basically just telling PyTorch you're gonna try to do unstructured pruning using L1 norm as your metric. So we put the amount, the ratio we want to prune for the convolutional layers as 50%, then 70% for the fully connected layer weight. So for the FC1 and FC2, we put the ratio of 0.7. So 0.7 or 70% is very, very aggressive. That's a lot of weights, or a lot of, yeah, what the model is learning. It's like it's gonna be removed. But that's because, as we saw before, FC1 has 500K parameters, way more than the convolutional layers. So, and FC layers usually can handle heavy pruning because they're often even over parameterized. So a lot of more modern CNNs now, they're mostly based on the convolutional layers itself, not really the FCs. So after you do this, what it does basically is it puts mask. It puts a binary mask on the weights. So the weights are still basically saved in your model. So we're not removing them from memory. This doesn't have any increase in efficiency, or it doesn't reduce memory size because it's still there. The weights are still there. You have to run prune.remove. So this is a very important step. So when PyTorch prunes, yeah, it keeps the weights, but it masks them to zero. Then when you do prune.remove, it makes this permanent. It actually deletes the pruning hooks, and it makes like the zeros be actually like real zeros. Without this step, the model can still like store and still hold the old weights. So after we prune, let's count how much parameters we have now. So as we can see here, we went from 545K parameters to 167K parameters left. The sparsity is almost 70%, but the accuracy dropped by a lot. As we saw before, the accuracy was around, the accuracy was around 71.11 for the baseline model. So we lost a lot of that because the accuracy now is 59%. So let's visualize what happens with the weight. What PyTorch did to the model after we did our unstructured pruning. So as we can see here, that all these weights close to zero were turned into zero instead. That's what the magnitude-based pruning does. So it doesn't care about the shape of the distribution or like which filter or which channel it came from, because it's unstructured. All it cares about is which weights are the closest to zero. That's what we'll be pruning out. So yeah, as we can see here, there's basically no weights near zero. All the weights that are near zero turned into zero instead. So since we put 50%, yeah, 50% of the weights for these layers were gone for the convolutional layers. Then for the fully connected layers, we put 70% for each. So it was able to prune out 70% for them. Then you can really see how there's that gap now between zero and like the other weights, because it really focuses on and tries to prune the zeroed weights, the weights near zero. Now let's visualize the sparsity pattern in the weight matrices, because as I talked about before, one of the big differences is the irregular patterns you can get in unstructured. That's why it's called unstructured pruning. So yeah, here we'll see that the black or dark pixels are the active weights, the non-zeros. Those are still in the model. Then the white pixels we'll see here are the prune weights. So what we'll be expecting is in the baseline model is going to be fully black because all of the weights are active. But when it becomes pruned in the unstructured way, it's just gonna have like white dots all over. It's gonna be random patterns also. So I just have a function for it. So yeah, we just process the weight matrices. Then since convolutional layers are usually 4D, we reshape it for 2D for the visualization. Then for FC layers, they're already in 2D. So we just create a binary mask, and that's what we show here in our graph. So yeah, as we can see here, it's very, very irregular. You can see the unstructured nature of magnitude-based pruning and unstructured pruning. So the zeros won't really form any nice patterns here. So they're very scattered. They're scattered to wherever small weights used to be. So these are usually the very small weights as we saw here. Then at the left side, we just see the baseline. So these are all the active weights. Then at the right, all the white spots here in this visualization are the weights that we pruned out. Very random. So another important step I talked about in the academic lecture and how important it is fine tuning. So when you're pruning, you're removing so much of what the model learned. You're basically just you're removing a lot of what it learned. So we try to gain it back through fine tuning. So I just have a simple visualization function here, helper function, to visualize the predictions before we do any fine tuning. As we saw, the accuracy was around 59%. So yeah, here we just have the true predictions versus the actual predictions versus what the model predicted, then the confidence level of it. So yeah, as you can see in this small subset, it's already made a mistake on 3 of them. Then we continue on. Because what's the use of making your model smaller also if you're not gonna try to keep the accuracy the same? It's like the main task it's supposed to do, it can't do well. So it doesn't matter if the size is smaller, right? That's why we do fine tuning. For fine tuning, basically you just retrain the model. We're just using the same training function we used for our original training, but we're training it for less epochs. As we saw a while ago, we trained it for 6 epochs. Usually you're gonna train a model for hundreds or a high number of epochs. When you're fine-tuning it again, you're just gonna train it for a smaller amount, a very little amount, because you're just trying to regain what you lost before. But when you do fine-tune, you're not turning the zeroed out parameters back into parameters that the model will use. Whatever is zeroed out before will stay zeroed out even after you fine-tune. So for now, since this is just a workshop, we're just loading it from a pre-trained. And we saw before that the accuracy was 59.38%. It dropped a lot. But after we fine-tune it again for 3 epochs, we were able to go back to 71% accuracy. Then as we see here, it even increased the accuracy, but that's just because it's a small subset. So the model just got a bit lucky. Usually after you prune, even after you fine tune, there's still a small drop depending on the use case. So now let's visualize the same model and the same images after we fine tune. So yeah, as we saw here, it was able to, it predicted 3 wrong. Then now we got 7 out of 8 right. So 73% now compared to the old 59% in this specific batch. So that's it for unstructured pruning and how to visualize what we've seen so far. Now let's apply structured pruning. So for structured pruning, we start off the same way. We're just here, I just copy again the original baseline model. then we're using this line, the LN structured, instead of L1 unstructured. So this parameter here, n equals 2, means we're using L2 norm instead, or the Euclidean norm, to score each filter. We're not scoring weights individually now. So in dim 0, because we're pruning along dimension 0, so the entire output channels or the filters. So when you prune out the whole filter, you're basically removing all the weights in that filter. The 3x3 by input channel block we had before. Then the corresponding output channel it has, then all the connections it has from that filter to the next layer. Notice that we're pruning here 50% from each convolutional layer, but we're not touching the fully connected layers this time. So structured pruning is most effective and meaningful for convolutional layers, where filters, because in the convolutional layers, filters represent distinct feature detectors. So you can see stuff like edge detectors or texture detectors and other things like that. So the trade-off we'll be getting is the overall like sparsity, or the overall amount of weights we're gonna prune out is a lot lower than the unstructured pruning, but the sparsity will be organized. So instead of it being random zeros all over, it will be entire rows or columns of zeros. It won't be scattered. So this structured pattern is also better for more standard GPUs and CPUs, because it can directly accelerate it. You don't need specialized libraries. Like what I said in my academic lecture, that's why usually out of the box, we use structured pruning. So yeah, as you can see here, we pruned out very little parameters only, because as we noticed, the fully connected layers had like 500K of it. So that's why it's a lot less we pruned. That's why I also chose a high amount of FC parameters. Then the accuracy drop is even more compared to unstructured pruning, because we basically remove entire feature detectors, right? So maybe this filter corresponds to a specific feature. If we remove that, that feature won't be detected properly by the model anymore. So that can lower down the accuracy by a lot. Now let's continue to visualize and see the difference of this compared to structured pruning. So this is these both here. So this is the baseline model again. Then we can see that even though it's like a lot smaller, the same like bell curve distribution is still kind of there. Then it's like the original form, it's still kind of untouched. The distribution almost looks the same as the baseline, because we're not really cherry picking individual weights. We removed complete intact filters. So let's say this specific filter has a low L2 norm. If it has a low L2 norm, that's basically what we're gonna prune. But what if the weights in that filter have weights scattered around? So it's like one is negative 0.4, one is near 0.2, one is negative 0.2. So it's scattered around. So if we remove that whole filter, it still keeps the weight distribution like almost the same. That's what I wanted to show here, compared to it in what we had before in our unstructured, where we're basically just removing everything close to zero. Now we're removing whole filters. So it's not just those closest to zero, it's whole filters. Then let's also visualize the sparsity pattern. As we saw before in the unstructured version, there's not really a pattern. It's very random. It's irregular, very sparse matrices. Now we'll see here that if we visualize it, those white strips, they're not random anymore. They're entire horizontal rows. That's the true difference of structured and unstructured pruning. So each white horizontal stripe here is an entire filter removed. So these black ones are still active filters, while the white ones are removed. So the original 32, we removed 16 of them. So basically, if you count these rows, it can still come up to 16. We pruned those filters. The entire row goes white. Every single connection it had on these filters is 0. It's not random. So when a filter survives, though, their entire row still stays black. So every connection remains active. See, there's no scattered white pixels anywhere, and filters are all or nothing, usually in structured pruning. So the zeros form clean, organized patterns, not random scattered dots, as we saw before in the unstructured pruning. Now, again, let's visualize predictions before we do any fine-tuning. This one had a very low accuracy, this model, right? After we did the structured pruning, it had 31% only. So yeah, here out of 8 images, it got 5 of them wrong, even more than the unstructured pruning. Then for fine-tuning, we basically do the same thing again, where we're training it for 3 epochs. But here we just load the model. In the actual notebook I gave, though, it will still train it for 3 epochs. So let's load that model. Then now it jumps up from around 31% to 70%. So the gain back we got from just 3 epochs is still huge. Now let's visualize it after we fine-tune for those same 8 images. So from 3 out of 8, it was able to get 7 out of 8 correct now. So the jump back in accuracy is almost negligible compared to the baseline what we had before. There, see? So the drop-off is huge because entire features or detections of the model are removed, but we're able to gain it all back after we fine-tune. Then as a final parts here of my notebook, I just have visualizations and graphs of what we saw so far. So the model accuracy for unstructured, baseline, and structured, there's been no difference here, barely any difference after we're able to fine-tune. Then for sparsity, unstructured is obviously a lot more because especially since we were able to prune the convolutional, the fully connected layers, which constitutes for most of the model. For unstructured pruning, yeah, the baseline, the accuracy dropped to 59% from 71%. But after we fine-tuned it, it was able to jump back up. And it's the same story for the structured pruning, but the structured pruning drops by a lot, mostly showing how important it is really to fine-tune, especially for if you do structured pruning. Now I just want to show just continue to show more visualizations because that's the most important for me when it comes to pruning, because this is how you see what to change and what to focus on. Since we saw the amount of parameters that each layer had, we saw that the FC1 layer had the most amount of parameters, so it's the most we can reduce. That's why we did 70% on it. Then as we see here, for our unstructured pruning, we were able to remove 46.5% of our parameters while keeping the same amount of accuracy. But for our structured parameters, only very little because once again, the FC layers, we didn't touch them because they're not good for structured pruning and they constitute for most of the parameters. That's why it still had 98% of the parameters. But it also shows how big of an impact it has on the convolutional layers, how big of an impact that has on the model's predictions. Then as a final comparison, I just have here one last visualization showing fine-tuning and like how it was able to predict properly after it got fine-tuned compared to before it got fine-tuned. So for this image at the first one, it's a ship. Then it predicted it as an automobile with a high confidence percentage. Then after tuning, it was able to predict it as a ship with a high confidence rating, while the rest of the percentages of like the automobile and airplane being basically 0. And the same stories for the rest of these predictions. That's all for my technical workshop. It was very simple process, but I just want to show how much of an impact these pruning techniques have, then how to visualize them for your own use case when you want to use pruning for your own models or your own projects.
Thank you, Rafael, for the presentation. I agree with the last statement, no. Even though it seems like the task is very easy or the way of implementing is very easy, the impact is big. And the visualization that you showed are actually very much helpful in understanding the context of removing the weights using pruning techniques. So the floor is now open for questions that the listeners might have. You have questions for Rafael? You can send it in the chat or maybe raise your hand if you have questions that you would like to ask. I actually have a question about the visualization that you showed in terms of the weight sparsity. The first one. Kasi the second one is very easy to understand. This one, could you interpret for the listeners, how should we look at this one? Kasi the other one is very easy to interpret na the y-axis that is one line corresponds to a feature map, right? And if it's all white, then it means that it's removed. And if it's black, it means that it's active. So how
Yes, sir. So it's for both visualizations, it's still the same. Where it's if it's white, any white dots basically on both visualizations means that that's a pruned weight. So all of these white dots here are just pruned weights. So yeah, it just shows how it's random pruned weights across the model. The reason why it's just horizontal in the other thing is because those pruned weights are full filters. That's why it's horizontal rows. But here it's more, since we're doing anything close to zero, all of these weights that are white are those that are just close to zero. We just remove them basically. So it just shows how it makes irregular patterns. And that's one of the reasons why people don't use unstructured out of the box, because it's like, since you're just removing random small weights, there's no big impact in your calculations and how the model calculates, like how your GPU will calculate the different things.
And you're not even removing the weights, you're just setting it to zero, right?
Yeah.
Yeah, I like this visualization and also the other one, the histograms that you showed. We have like one question here from Gab. What use cases would pruning work best or perform badly?
So pruning can work for any use case. That's one of the things I talked about in my academic lecture, where uh, pruning works for every use case, but we don't have a universal general way to prune. That's why one of the problems with pruning now is because if you have a specific use case, you have to build it from scratch. You have to do lots of different experiments or different tests. That's what I wanted to show here also, that you have to visualize what you're doing to your models to be able to read and see why it's performing badly, why it's performing good, so you can continue in that aspect. For the good baseline still though is to always try to prune, use structured pruning, then fine tune it first, then try to go from there if you need any more specific implementations.
I also do not have like a general answer to say that if we're performing it for this certain task or this certain domain, it will not work or it will work better. I think similar to the answer of Rafael, you have to, when you're performing things like this, you do not just perform them out of the box. That you're going to use a technique or use a function to drop your weights or prune your weights without understanding which weights were pruned. So it's very important for you to show visualizations like this that could help you understand what's happening when you're removing certain weights or certain filters certain output feature maps for your projects or for your the problems that you're trying to solve. So I don't think there's a universal answer to say that it will perform best if we have like this specific problem or this specific task that we're performing, or it will work um, a bit worse if we're performing a specific task or specific domain. Okay, but that's a good question. The main important thing here is you do it incrementally maybe, then see if it's performing well or if you're still achieving the performance that you have. I think um, a piece of advice, maybe the first thing that we need to do is we have to make sure that the performance using the whole model should be good first before we try out removing some features. So we only use this if and only if there are applications that we want to make sure that the model can be used on, let's say, edge devices or instances wherein we want to make the model um, useful for certain applications which requires small footprint instead of directly applying this um, at the start of your training. So train a good model first, then you go from there. Okay, in trying to remove or make your model smaller. Okay, I think there are no more questions for Rafael. Thank you for this presentation. We're now going to move to the last one,